In this paper, we propose a method called MoGA, which demonstrates how we reconstruct a Gaussian avatar from a single view image. Given a single input in the wild image, MoGA captures the detailed 3D shape and consistent appearance represented by 3D Gaussians. Furthermore, the resulted 3D avatar can be animated naturally with unseen poses. Existing methods struggle with such in the wild cases, sometimes missing body parts like hands and feet, or introducing artifacts in facial regions. Without direct supervision, these methods tend to produce distorted geometry and inconsistent textures, especially in side views. Unlike existing methods, MoGA generalizes well to real-world images, even in outdoor settings with complex backgrounds. Additionally, it handles diverse clothing styles, including loose skirts or jackets, making it more applicable to more real-world scenarios. This model is also robust to challenging human poses and can be directly applied to humans in motion. Finally, we demonstrate animations of our reconstructed avatar. Notably, they are only learned from one single image. The challenge of the problem stems from the ill-posed nature of monocular Gaussian avatar reconstruction, which leads to depth and appearance ambiguities. To address this, recent approaches use 2D multi-view diffusion models to hallucinate unseen views. However, these synthetic images are often sparse and lack 3D consistency. As a result, the final 3D reconstruction appears unrealistic and blurry. While diffusion models improve generalization, they introduce 3D inconsistencies and artifacts in unobserved regions. To address this, we propose to leverage a 3D generative avatar model as a complementary prior. Sampled from the learned distribution prior, our model can generate 3D avatars with different identities and clothing styles, and from different viewpoints. In addition, our generated human can be animated with unseen poses. By projecting images into the latent space of this generative prior, we naturally enforce 3D consistency while incorporating additional shape and appearance constraints. By jointly leveraging 2D diffusion models and 3D generative priors, MoGA reconstructs realistic and detailed Gaussian avatars. Next, we introduce our method. First, we learn a 3D generative avatar model from a 3D human dataset. This model represents avatars with 3D Gaussians in canonical space to capture both shape and appearance. A deformation module then transforms this representation into the pose space for rendering. To train this model, we optimize a Gaussian autodecoder and a latent diffusion model by a single-stage training pipeline. At test time, we first generate synthetic images from the multi-view diffusion model. Avatar creation is then formulated as a model inversion problem by fitting the learned generative avatar to these images. We initialize the latent code by image-guided sampling and optimize it through model inversion, while keeping the decoder and diffusion model fixed. Both the avatar model and pose parameters are optimized in an alternating manner to correct abnormal poses. We compare MoGA with current state-of-the-art methods. As shown in the video, existing methods struggle with missing body parts, like hands and arms, especially under self-occlusions. These artifacts become more pronounced in side views due to limited observations. In contrast, our method can reconstruct 3D consistent appearance and geometry without distortions. Here we compare against PS Human on more challenging subjects. Due to its fixed topology of a template mesh, PS Human fails to capture topology changes, such as the gap between the arms and face. On the right, we show an example of reconstructing a ponytail. Unlike mesh-based approaches, our method reconstructs a Gaussian avatar from single input image. This more flexible representation allows us to reconstruct more complex and detailed structures. Finally, we present additional qualitative results and summarize the method. In summary, MoGA reconstructs high-quality, animatable 3D avatars from a single image. By leveraging a generative avatar prior, it outperforms previous methods in realism, detail, and robustness while demonstrating generalization in the wild images. Thank you for watching.